So this is the range. This is very easy to calculate. Unfortunately, if I have outliers in my data, it makes the range almost useless. So then we have to go back to our original question. How can we measure how spread apart our data is without kind of being susceptible to the outlier problem, or at least reduce our sensitivity to the outlier problem? And the answer to that question is something extremely important in statistics, and that is the concept of variance. That's the concept of variance. All right, so we've done the range, we've figured out how to do that. Now we're going to try to calculate something called the variance, which is going to tell us how spread apart the data is in a way that's not quite as susceptible to outliers. So that's very, very important. And the concept of variance, I'm going to tell you right now, along with standard deviation, which we'll get to in a little bit, the concept of variance is never going to leave you in statistics. So you really need to make sure, just like understanding the mean, very important. Understanding the variance, extremely important. So instead of just putting down the equation for variance, which I could do and be done, I'm going to lead you through a logical kind of walkthrough of what it means. And so that way you'll know what the equation is for variance, but you'll also know in your gut what it really means, because that's what you really need to think about. And that's what you really need to internalize. So let's say that you have some data set. I'm just kind of drawing a picture here. And this could be a list of numbers. It could be the height of people in a room, could be the age of people, could be their, if they like peanut butter more than jelly. It doesn't really matter. But usually it's numerical data. So for the kind of the sake of argument, think of it as the ages of people in a room or something like that. So we've learned in this course so far that when you have a bunch of data, we can calculate the mean. And the mean is kind of like the middle of the road value, right? It's kind of like a representative number that kind of just cuts right to the middle of the data set, the center of gravity, so to speak, of the data set. And we use the X bar notation when we're talking about sample data, right? This is the sample mean. And the way you get it is you add all the values up in your sample and you divide by the number of samples, and then you get that number that represents the mean of the sample. All right, so if I wanted to look at each data point, visualize this cloud as a bunch of data points. We've got some data points here, some data points here, which are different values, and here is kind of the mean. Now, if I wanted to look at each individual data point and figure out how far it is from the mean, then I'm kind of measuring the spread of each individual data point, right? Because remember, what we're trying to do is we're trying to figure out how spread out our data is. So instead of just doing the range, which is the endpoints, we want to look at every single data point in our set, figure out how far away it is from the mean, and somehow roll that into a calculation that we can then calculate the variance, which is how spread the data is. So if we're just going to examine one point, and only one point right now, then what we would find is for each point, for each data point, the deviation from the mean is very, very simple. Nothing too complicated here. The data value minus the mean. I mean, that's very, very simple, right? So in other words, if I have a data point here, it's 1, and I want to figure out how, and the mean is like 5, then if I want to figure out the deviation from the mean of this data point, I'm just going to subtract them. I'm going to take my data point, I'm going to subtract away the mean, and that's going to give me how far away it is from the mean. If I've got a data point over here like 7 and the mean is 5, well then I'm going to take that 7, I'm going to subtract 5 away. That tells me how far away that point is. So you might think that by looking at each individual data point, subtracting the mean from it, that gives us a nice indicator of the spread of the data. And you would be right. So one way that we might roll it into one calculation, what we might want to do is add up all of these little deviations from the mean of every single data point in our set. When I say x sub I, instead of being scared by that, what you need to think of is x sub I is just the ith data point. I have maybe 5 data points, so I sub 1, I sub 2, I sub 3, 4, and 5. Those are just the individual data points. So when you see something like x sub I minus the average value or the mean, x bar, what you're doing is you're taking every data point, subtracting the mean, and then you get that number, and you do it again and again for every single data point. You're subtracting from the mean. You get those differences and you add them up. That's what the sigma does over here. You add them up. So if we add up all these differences from the data points to the mean and then divide by the number of data points that we have, then what we've really done is we've averaged the deviations of all the points from the mean. Now I'm going to say that again. It's so incredibly important, right? What we've done is we've taken every data point, we subtract the mean. That gives us the deviation of every point in our set from the mean, okay? Then we add up all the deviations and we divide by the number of points. So what we're doing is we're averaging the deviations of all of our points about the mean. We're getting an average value. This is a nice way to represent the average, variance is what we're calling it, from the mean. It gives us the spread of the data because we're not just looking at the endpoints like with the range. We're looking at every point, finding out how far away it is from the mean, and we're getting all those differences from the mean, and then we're averaging them all because all the points are equally weighted, and so we get a number out of it that tells us, if we get a really big number, it tells us, yeah, a lot of these points are far away from the mean. If we get a really small number in this calculation, it tells us, yeah, all these points are kind of close to the mean because all the deviations were really small. That's what we're doing here. All right, so let me write a couple things down here. I'm just going to kind of put what I have on my page. This does the averaging. Right? Now, this is not the final answer of what we really want to do to calculate the variance, because there's one big problem with this, but the thought process is what's important here. We're going to make one change to this and then we'll be done. The problem is, notice that we have data on the left-hand side of the mean and data on the right-hand side of the mean. You're always going to have that because the mean, by definition, is kind of like the center of your data set. It's a calculated value that kind of is at like the center of gravity of your data set. Kind of there's some points below it and there's some points above it. That's always the way means are, right? So if I have the calculation written as the data point minus the mean, then for all of these data points over here, let's pretend the mean was 5. All of these data points are greater than 5. So then one of the data points might be 7 minus 5. And then another data point might be 10 minus 5. And then another data point might be, 6 minus 5, and then maybe 12 minus 5. There could be lots of data points. The mean is always the same, and you're subtracting the data value minus the mean, right? But then look what happens on the other side of the mean. All of these data points are actually smaller than the mean. So if we actually do this calculation, then I'm going to have some points over here minus the mean. So if this mean were 5, and the data points are here are smaller than 5, I could have 3 minus 5. I could have 2 minus 5. I could have 4 minus 5. In all of those cases, 3 minus 5, 2 minus 5, 4 minus 5, I'm going to get a negative number on the top because I have a small number minus a big number. So the problem with doing this calculation, even though it makes perfect sense to us, is that half of the data points are going to give us negative values on the top. The other half of the data points are going to give us positive values on the top. So since I'm adding them all together and half of the data points are going to give me negative deviations and the other half of the points are going to give me positive deviations, when I sum them all together in this calculation, I'm going to always get 0, which is not what I want. I want to find a number that represents the spread of the data. And although it makes perfect logical sense, because I'm subtracting the mean and because the mean's always in the middle, I'm always going to get negative values on the top along with positive values, and so I'm always going to end up getting 0 if I do this calculation as is. So to cut to the chase, we're going to make a small modification, and we're going to call this the variance, which I'll explain this in a minute, but it's called the variance. Right? And it is exactly what I have written before. You have sigma x I minus the average value, or the mean, divided by capital N. Everything is exactly the same, but we make one change. We square this guy right here. This is what we call the variance. In fact, I'm going to write it as population variance. So I'm going to circle this because it's very, very important. Population variance. This is a core, statistical concept. It really is. It's like if you're studying algebra, you have to learn about X and Y. Well, if you're studying statistics, you have to learn about variance. It is absolutely, fundamentally central to everything that we're going to do now and everything to follow. So you need to make sure you understand it. what we've done is we've done exactly the same calculation. So all of the logic that I spent a lot of time explaining to you is true. The only thing that we did is we take the sample value minus the mean, and we get the number, and then we square it. So we're getting the deviation from the mean, and then we square it. And then we do that for all data points. So if your mean is 5, you might have 6 minus 5, and 7 minus 5, and 8, and 10 minus 5. And you're squaring each of those differences, okay? So then on the right-hand side, we get positive deviations. We're going to square them. They're going to get bigger. On the left-hand side, when we have these negative issue that pops up, 3 minus 5, 2 minus 5, 1 minus 5, we would get negative values, but we square it. The squaring action makes it positive. So we get all of the deviations of all of the points from the mean, and we square them all. You do the squaring first, right? In fact, it might even make more sense if you want. You could put a little bracket around here if you like, just to kind of show that the squaring action is done before any of the addition. So for every data point, we subtract from the mean, we square it, and then we do that for every data point, and we add them all up, and we completely sidestep the problem of having half negative values and half positive values leading to nowhere, leading to 0. So no matter what your data points are, you're always going to get a positive value on the top. You divide by the number of samples. This is averaging the deviations. You're still averaging the deviations. The only thing is you're squaring them first just to get around this whole negative issue that we talked about. So this is called the variance. The symbol here is actually a sigma. So let me write that down for you. This is sigma. This is also sigma. This is a capital Greek letter called sigma. This is a lowercase Greek letter sigma. The reason we have the square here is just to remind us that this is a measure of the deviation, which we're calling the variance in this case, variance about the mean, but all of these variances are squared, and so that's why the square is there. It's just to remind you, it's not to tell you to calculate anything more, it's just to remind you that this is actually modeling a variance of all the data that falls around the mean and how spread apart it is, but we've kind of modified the actual difference and we've squared everything, and we did that so that we didn't get a 0 answer. So it's very common in a book, you'll see sigma squared all over the place. When you see this symbol in a book with a square like this, you just need to replace it mentally in your head with, oh, this is just a spread of the data. The bigger this number is, whatever I've calculated, the more spread out the data is. The smaller that number is, the closer that data is packed. And when I say the closer it's packed, I mean the closer it's packed around its mean. When I say the farther spread apart it is, I mean the farther spread apart it is about its mean. All right? One more thing I want to say before we close. This is a population variance, okay? Population, it means that all data points in our population, that's what population variance is, right? But don't forget that we're in the business of taking samples, right? So the sample, because you're probably never going to know the population variance. You're not going to know all the data points. So in reality, what you do is you take a sample. We've talked about this many times, and you arrive at S squared. You have to choose a different symbol, right? Because this is the sample variance. I told you a long time ago, you need to understand the difference between a sample and a population, and this is the reason why. So this is exactly the same thing over n minus 1. All right, and this is called the sample variance. Now notice there's one major difference here. There's two major differences. The sample variance represents how spread apart the samples that I've taken are about the sample mean, all right? The sample mean is denoted x bar, okay? We're doing it, the same calculation. The reason it's n minus 1 on the bottom, this is the number of samples I have minus 1. That's just a convention. The reason why there's a minus 1 here goes way beyond the scope of this class. What you need to remember is that when you have a sample, a finite set of samples, you have n minus 1 on the bottom when you're doing this calculation. When you have the entire population at your disposal, and for some reason if you knew all the data points in the population, then you would divide by n, the total number of people in the population. Now one thing I need to modify here, just as I did my description, I showed you all this stuff because I was trying to kind of make it really clear for you. Since this is a population variance, okay, instead of x bar, the better way to write this, the way that you would see it in your book, is minus mu, right? Since it's a population variance. because remember, when we talk about populations, the population mean we call mu. The sample mean we call x bar, like this. So this is the most important thing to this lesson, and I want you to try to internalize it, try to understand it. Follow me on to the next lesson. We're going to work more problems when we're actually trying to calculate these variances. The most important thing for you to know is that all data is going to have a certain amount of dispersion or spread, right? When you talk about spread, you really care about how spread apart it is about its mean. That's what you really care about. Right? When you have samples, when you have actual data you've gone out and collected, then you have a sample mean, which we know how to calculate. We take the difference between every data point and its sample mean, we square the differences, we divide by the number of samples minus 1. That gives us something s squared. Notice sample variance, s goes with s, so sample and s. So that when you see s squared, you know that it's the variance of the samples that you've taken, right? That's how you do that calculation. For a population, which is everybody, if you knew the actual population mean, and if you knew every single data point of the population, like every person in the United States of America, then you could calculate the population variance, which is denoted by sigma squared. So in both cases, the calculation is very, very similar. It's just in the population case, we are dividing by the number of people in the population. In the sample case, we're dividing by the samples minus 1. But fundamentally, it's the same sort of thing. Most important thing you need to know is when you see a sigma squared like this guy, you need to think population variance is talking about our population. When you see an s squared like that, you need to think they're talking about our sample that we've taken. And that's why I took so much time earlier to make sure you understand the difference between a sample and a population, and a sample mean and a population mean, because in this case, the calculation is actually different from the population to the sample. So make sure you understand this. Follow me on to the next section where we will get some practice calculating these things, and you'll find that it's not very hard.